Okay, hello everyone in a new video, which is the part 2 of chapter 10, Archimedes upthrust. In this one, we are going to solve exercises on what we have explained previously in part 1. So let's start by exercise number 2. So already in part 1, we have, at the end of the video, we have solved exercise number 1, and this is exercise number 2. So in order to determine the density of an alcohol, we take a solid S suspended from the free end of spring balance and two containers, one containing water and the other alcohol. So take G is equal to 10 Newton per kilogram, which means that we are performing this experiment on Earth, on the surface of the Earth. Part 1, real weight of S. S is in equilibrium in air. So notice that until this moment they didn't mention anything about documents 1 and 2, so we are not allowed to use them. So S is in equilibrium in air. The spring balance indicates 80 Newton. This indication represents the value of W of the real weight of Sy. So knowing that the solid S is attached to the free end of the spring balance and it's in equilibrium in air, so 80 Newton represent the real weight of the solid S. Then let's say here we are in part 1. Since the suspended object, which is given by S, is in air at equilibrium, then the spring balance indicates its real weight. Then in this case the real weight is given by 80 newtons. So let me write here that the real weight is given by 80 newtons. Now part 2, volume of S. We immerse S completely in water of density ρ is equal to 1000 kg per meter cube. So we know that the density of water is given by 1000 kg per meter cube. And they mentioned document 1. Now we can only use document 1. The spring balance then indicates 7 Newton. So with the solid S, so here we have it's completely immersed in water. So what does this mean? That the volume VI of the immersed part, so this is the volume of the immersed part, is equal to the volume of the solid S, which is V. So this is the solid S completely immersed in water. The spring balance in this case indicates 7 newtons. So number 1, what does the indication of the spring balance indicates? Knowing that solid S for sure being at equilibrium in water, so in this case the spring balance indicate the apparent weight. So always the spring balance indicate weight, but in this case because the solid S is in water and not in air, so the spring balance indicates the apparent weight. And then let's say since the suspended object, which is S, is in liquid, which is water. So let's say it's immersed in a liquid. And at equilibrium. Here it's important that we should mention immersed in a liquid and at equilibrium. The same for part 1, it's important to mention that the solid S is in air and at equilibrium. Then the spring balance indicates its apparent weight. So in this case the apparent weight is given by 7 newtons. So this is the apparent weight when the solid S is immersed in water. So here let me write that. The apparent weight is given by 7 newtons. Now number 2, calculate the value of F of the Archimedes upthrust exerted by water on S. So here, because we have the real weight and the apparent weight due to water, then we can calculate the value of F due to the Archimedes upthrust, because it's the difference due to both indications, so the real weight minus the apparent weight. Here no need to mention any law, because this is the definition of F upthrust, which is denoted in this case to be F not F up. So it is 8 minus 7, which is equal to 1. Since both the real weight and the apparent weight are in newtons, so the value of F will be in newtons. Then F is equal to 1 in newtons. Now in number 3, deduce the volume V of S, and by deduce it means that we need to use the part just previously before. In number 2, we have determined the value of F, and we are interested in determining the volume of V of S, knowing that the volume and the value of F are related via the following formula, that F is equal to the density of the liquid multiplied by the volume of the immersed part multiplied by G. So here, knowing that because S is completely immersed in water, so this is the volume of the immersed part, so which is equal to the volume V of the solid S. So here let's say, since S is completely immersed in the liquid, and then Vi is equal to V. So I will continue this part here. Now let's rewrite this formula, but replacing Vi with V. So we have that F is equal to the density of the liquid rho L multiplied by V multiplied by G, knowing that we are interested in calculating the value of V. So constructing the triangle of this formula, here because we have multiply, then F will be at the top, rho L, V and G at the bottom. We are interested in calculating V. So V is equal to F divided by the density of the liquid, which is denoted here in this case to be rho, which is water, multiplied by G. And the value of F is given by 1, the value of rho is given by 1000, and the value of G is given by 10. Plugging this fraction on the calculator, it will give me 1 times 10 to the power minus 4. Since everything in the SI, so the unit of V will be in the SI, which is meter cube. So the volume V of the solid S is given by 1 multiplied by 10 to the power minus 4 meter cube. So now we have that the volume V of the solid S is given by 1 times 10 to the power minus 4 meter cube. Now part 3. Now S is completely immersed in alcohol, document 2, so they mentioned document 2, now we are allowed to use it. The spring balance indicate in this case 7.2 newtons. So what does 7.2 newtons represent? It represents the apparent weight. So here we have two apparent weights. Let me write that W apparent prime is equal to 7.2 newtons. So what's the difference between this apparent weight and this apparent weight? This apparent weight is due to water, and this apparent weight is due to alcohol. So if we are using this apparent weight to calculate F, the magnitude of the Archimedes upthrust, so we are calculating the value of F due to water on the solid S. If we are using we are using this apparent weight to calculate the magnitude of F, so in this case we will be calculating the magnitude of F exerted by alcohol on the solid S. They are telling me to calculate the value of F prime of Archimedes upthrust exerted by the alcohol on S. So because here we are determining the value of F prime due to alcohol, then we will use this apparent weight. Then the value of f prime, which is given by always the real weight minus the apparent weight. So in this case, the real weight will not change. It is given by 8 minus the value of the apparent weight, which is given by 7.2. Now, in this case, the value of f prime is given by 0.8. Since both the real weight and the apparent weight are expressed in newtons, so the value of f prime is in newtons. So f prime is equal to 0.8 newtons. So what does this value represent? It's the force exerted by alcohol on the solid S, because here W apparent is due to alcohol and not water. Now in number 2, deduce the value rho prime of the density of this alcohol. And by deduce, it means that we need to use the part just previously before. And we know that f prime and rho prime are related via the following formula. So the value of f upthrust is equal to the density of the liquid multiplied by the volume of the immersed part multiplied by G. So we are interested in calculating the value of rho L. So constructing the triangle of this formula, here because we have multiplied and f upthrust will be at the top, rho L, Vi and G at the bottom. Knowing that we are interested in calculating the density of the liquid, which is in this case alcohol, which is denoted by rho prime, which is equal to the value of f upthrust due to alcohol, which is denoted by f prime, divided by Vi multiplied by G. And here for the same reason, because when the solid S is immersed in alcohol, it's being completely immersed, then the volume, this is the immersed part, in this case the volume of the immersed part is equal to the total volume of the solid S. So let's say that between brackets, since S is completely immersed in alcohol, or let's say in the liquid, then Vi is equal to V. What is the value of V in this case? We already determined from the second part of this exercise, which is given by 1 multiplied by times 10 to the power minus 4. Now let's rewrite this formula, replacing Vi by V. So the value of rho prime is given by f prime divided by V multiplied by G. Now the value of f prime is given by 0.8. The value of V is given by 1 times 10 to the power minus 4. And the value of G is given by 10. Now plugging this fraction on the calculator, it will give us 800. Since everything in the is expressed in the SI, f prime, V and G, so the value of rho prime will be in the SI, which is kilogram per meter cube. So the value rho prime, which represents the density of this alcohol, is given by 800 kilogram per meter cube. And now let's move to the next exercise. Exercise number 3. Consider a metallic solid S that bears the inscription 100% copper, 8,900 kilogram per meter cube. So before we continue, what does this indication mean, or inscription? So this quantity has the following unit, kilogram per meter cube. So this unit is the unit of density. So this value represents the density. So the density of copper. So they are claiming that this metallic solid S is 100% made up of copper. In order to check whether the inscription about the density is true or no, we perform the following experiment. So here they are telling us that this indication is the density. Now the first experiment. In order to determine the mass of S, we suspend it from spring balance by means of a thin string. This is the string. So here they mention the string, for sure we have tension. The solid S takes then an equilibrium position under the action of two forces. So here the solid S being at equilibrium, so at any moment we can use the condition of equilibrium. Number 1. Give the name of these two forces that are acting on the solid S. So because the solid S has a mass, as mentioned here, then it will be directly subjected to the weight, vertically downward at the center of gravity. And because we have a string, it will be subjected to the tension force. Then the two forces are given by the weight W and the tension T. Number 2. Give the relation between these two forces. So they are asking me about the vector relation. In other words, the condition of equilibrium. So how do you apply this condition? We always start by writing at equilibrium as a title. Then on the left, we write the sum of forces acting on the solid S, and they are given by the weight and the tension. Then the weight vector plus T vector is equal to the 0 vector. We don't forget the 0 because this is a vector. We don't forget the vector because this is a vector relation. And moving T to the right hand side, so W vector is equal to minus T vector. Now what does the first equation tells us? It tells us that both forces acting on the solid S, the effect of them, cancel each other in order to give us the equilibrium, which is the 0 vector. So this is the first equation. And the second equation tells us that both forces have the same line of action, opposite direction, and same magnitude. Now number 3, referring to the reading of the spring balance, give the value of the weight of S. So knowing that this experiment, okay, they didn't mention document 2, we are not using document 2, we are using only document 1. Knowing that from document 1 that the solid S is being at equilibrium in air, so the spring balance indicates the value of the weight because it is at equilibrium and in air. So referring to the reading of the spring balance, give the value of the weight W of S. So here let's say, since the suspended object, which is S, is at equilibrium, in air, then the spring balance indicates its real weight. So here the real weight is given by the indication of the spring balance, which is given by 8. And because we are taking data from the spring balance, we multiply by the scale, which is given by 1. So this is given by 8. Since the scale is expressed in newtons, so the value of the real weight will be in newtons. So the real weight is equal to 8 newtons. Now, in number 4, calculate the mass m of the solid S, take G is equal to 10 newtons per kilogram. Knowing that the weight and the mass are related via the following formula, we are interested in calculating the value of the mass. So here, because we have multiplied and W will be at the top, m and G at the bottom, we are interested in calculating the value of m. So m is given by the weight, which is denoted by the real weight, divided by G. The value of the real weight is given by 8 and the value of G is given by 10. Plugging this fraction on the calculator, then the mass is given by 0.8. Since both the real weight and the G are in the SI, so the value of m will be in the SI, which is kilograms. So now here we know that the mass of the solid S is given by 0.8 kilograms. Now, second experiment, solid S kept suspended from the spring balance is immersed in a test tube containing water of density 1000 kg per meter cube. So the density of water is given by 1000 kg per meter cube. So they mentioned document 2, now we are allowed to use it. The reading of the spring balance changes. Number 1, reading the indication of the spring balance give the value of the apparent weight of S. So here they are already telling me that the spring balance indicates the apparent weight. Let's justify why the spring balance is indicating the apparent weight. So let's say since the suspended object S is immersed in a liquid, as we can see here that the liquid they mentioned is given by water, and for sure it is at equilibrium. Then the spring balance indicates its apparent weight. So in this case the apparent weight is given by the indication of the spring balance, which is given by 7. And because we are taking data from the spring balance, we multiply by the scale, which is given by 1. Since the indication is expressed in newtons, so the value of the apparent weight will be in newtons. So W apparent is given by 7 newtons. And knowing that previously the real weight was given by 8 newtons. Number 2, give the name of the force that led to a different indication on the spring balance and calculate its value. So because we have a fluid or a liquid in particular, which is water, then the solid S will be directly subjected to Archimedes upthrust. So the name of the force is Archimedes upthrust force, F upthrust. And here in the same question they are telling me and calculate its value, knowing that we have the value of the apparent weight and the real weight. So the value of F upthrust, the magnitude, which is the fourth property, is always given by the real weight minus the apparent weight, which is given by 8 minus 7, which is equal to 1. Since both are expressed in newtons, so the value of F upthrust will be in newtons. Then the value of F upthrust is equal to 1 in newtons. And now number 3, calculate the volume of the displaced water, deduce the volume V of S. So we know that the volume of the displaced water, or the immersed volume, which is the same, and the value of F upthrust are related via the following formula. F upthrust is equal to the density of the liquid times the volume V of the immersed part times G. So we're interested in calculating the value of VI. So here VI, which is the immersed volume, it's the same of the volume of the displaced water. So constructing the triangle of this formula, here because we have multiplied, then F upthrust will be at the top, rho L, VI and G at the bottom. We are interested in calculating the value of VI. So putting our hand over VI, VI is equal to F upthrust divided by rho L and G. So here the density is denoted by rho multiplied by G. The value of F upthrust that we already calculated is given by 1. The value of rho is given by 1000, which is water, and the value of G is given by 10. Plugging this on the calculator, it will give me 1 times 10 to the power minus 4. Since everything in the SI, so the value of VI will be in the SI, which is meter cube. Now we have that VI is equal to 1 times 10 to the power minus 4 meter cube. But here in the same part they are telling us deduce the volume V of S, and by deduce it means that we need to use the part just previously before. Number 3, we have determined the volume of the displaced water, or the immersed volume. So because here the solid S is completely immersed in liquid, this is the immersed volume. So it will be equal to the volume V of S. So in this case, let's say since S is completely immersed in the liquid, so usually they give half a mark for this statement, then in this case V is equal to Vi is equal to 1 times 10 to the power minus 4 meter cube. So the volume V of the solid S is given by 1 times 10 to the power minus 4 meter cube. So here we have that the volume V of the solid S is given by 1 times 10 to the power minus 4 meter cube. Now here if we look at the given, so we have determined the mass corresponding for the solid S. We have the volume V corresponding for the solid S. So which physical quantity we can calculate using these two is the density rho, which is the aim of this exercise because we need to check whether this inscription is true or no. Now, number 1, deduce the density of the substance of S. We are in part C, which is the conclusion, and here by deduce it means we need to use the results of both experiments 1 and 2 because there is no previous part in part C. So in part A of this experiment we have determined the mass, and in part B we have determined the volume, knowing that the density of the solid S can be calculated using mass over volume. So the mass, which is given by 0.8, and the volume V, which is given by 1 times 10 to the power minus 4. Plugging this fraction on the calculator, it will give us 8,000. Since both the mass and the volume are in the SI, so the unit of rho will be in the SI, which is kilogram per meter cube, the same as for water. So this is the density of, this is the unit of the density of water, kilogram per meter cube. All densities have the same unit, which is kilogram per meter cube. So the density of the solid S, let's denote it by rho S for the solid, is given by 8,000 kilogram per meter cube. Now number 2, the final part in this exercise, is this inscription about the density of S true or false? So by this inscription, the inscription, they are referring to the inscription and the text of this exercise, which is 100% copper, 8,900 kilogram per meter cube. After performing this experiment, we have determined that the density of the solid S is given by 8,000 and not 8,900, which means that the following inscription is false, because since the density of S is different than the density of copper, between brackets, let's say 8,000 kilogram per meter cube is different than 8,900, then the inscription is false. And by this we have finished solving this exercise. Let's move to the next one. So exercise number 4, consider a solid cube S of side A is equal to 3 centimeters. Knowing that centimeter is not the SI unit of length, in order to convert from centimeters to meter, we divide by 100. Then the side of this cube is given by 0.03 meters. We suspend S at the lower extremity of spring R. The extremity of the spring is fixed to a support adjacent figure, so they mentioned this figure, now we can use it. The stiffness of the spring is K is equal to 10 newtons per meter. So K is equal to 10 newtons per meter. So what does this stiffness represent? In order to elongate this spring by 1 meter, we need to apply a force worth of 10 newtons. Take G is equal to 10 newtons per kilogram. At equilibrium, R is elongated by delta L is equal to 7.3 centimeters. So here, at any moment, we can use the condition of equilibrium. Moreover, they are giving me the elongation of the spring. So delta L is equal to 7.3 centimeters, knowing that also centimeter is not a unit of length. In order to convert from centimeters to meter, we divide by 100. So the elongation is given by 0.073 meters. Number 1. Determine using Hooke's law the magnitude T of the tension T vector of the spring. Here, because we have a spring, then the solid S will be subjected to the tension in addition to the weight. And they are telling me using Hooke's law because we have the stiffness and we have the elongation. Then whenever we need to use the law, we need to mention the law that we are using. Apply Hooke's law. Hooke's law is given by the tension T, which is equal to the stiffness multiplied by the elongation, which is denoted by delta L. The stiffness is given by 10 and the elongation by 0.073. Since both are in the SI, so the value of T will be in the SI, which is in newtons. Then the value of T is given by 0.73 newtons. And now in number 2, S is at equilibrium under the action of two forces, its weight W and the tension T. This is important. 2.1, give the condition of the equilibrium of S. So always we start by writing the title at equilibrium. How do you apply this condition? Always on the left we write the sum of forces acting on the solid S, and they are given by the weight and the tension. And on the other side we write the equilibrium, which is the zero vector. Now moving T to the other side, to the right hand side, it will gain a minus sign, so the W vector is equal to minus T vector. So this is the condition of equilibrium. And now in 2.2, deduce the magnitude W of the weight vector, W of S, and by deduce it means that we need to use the part just previously before. In 2.1 we have determined the condition of equilibrium, which is given by W vector is equal to minus T vector, and we can deduce the value of the weight because we already know the value of the tension, knowing that this equation tells us that both forces have the same line of action, opposite direction, and same magnitude. We are interested in the magnitude, so let's say in magnitude. And now we drop the vectors and we remove the minus sign, knowing that the tension T is equal to 0.73 newtons, then the value of W is equal to 0.73 newtons. So here, in addition to this given, we have that the value of W is given by 0.73 newtons. Now in number 3, show that the volume of S is V is equal to 2.7 times 10 to the power minus 5 meter cube, knowing that we have the side of the cube, which is 0.03 meters. Because this is classified as a regular shape, so the volume V is given by the side of the cube A to the power 3. So we use the SI unit of the side and not the 3 centimeters, 0.03 to the power 3. Plugging this on the calculator, indeed it will give me 2.7 times 10 to the power minus 5. Since the side here that we have replaced is in the SI, so the volume V will be in the SI, which is meter cube. So the volume V is given by 2.7 times 10 to the power minus 5 meter cube. Now number 4, S is now totally immersed in a liquid. This is important. So whenever it is totally immersed in the liquid, we know that the volume of the immersed part is equal to the volume of the solid S in a liquid of density rho L. The magnitude of the tension of the spring becomes T prime is equal to 0.41 newtons, knowing that we always have that the weight is equal to the tension because it is at equilibrium. This equation we have used here. This variation is due to the Archimedes upthrust force F exerted by the liquid on S. Give the line of action and the direction of F. We know always that F acts vertically upward, opposing the force of gravity. So the line of action is vertical. And the direction is upward. 4.2. Show that the magnitude of F vector is F is equal to 0.3 newtons. So here they are asking me about the fourth property of the building, which is the magnitude. So here we have the value of the real weight, which is given by, notice that in number 2 we have, in 2.2 we have determined the value of the weight. So because this experiment was being performed in air, so the value of the weight was given by 0.73 newtons, which is equal to the tension. And now they gave me the value of T prime, which is equal to 0.41 newtons. So here in this case, the value of T prime represents the apparent weight, because always we have W is equal to T. So this tension is when the solid S is immersed in the liquid. So this T prime represents the apparent weight. So this is the real weight and this is the apparent weight. So from this part we know that the real weight is given by 0.73 newtons. So the value of F can be determined using real weight minus apparent weight, so which is equal to 0.73 minus 0.41, which is equal to 0.32. Since both the real weight and the apparent weight are in newtons, so the value of F will be in newtons. Then the value of the Archimedes upthrust force, the magnitude, is given by F is equal to 0.32 newtons. Now in 4.3 determine rho L, knowing that rho L and F are related via the following formula. F upthrust is equal to rho L multiplied by volume of the immersed part multiplied by G. We are interested in determining the value of rho L, the density of the liquid. So constructing the triangle of this formula, so here because we have multiplied and F upthrust will be at the top, rho L, Vi and G at the bottom. We are interested in determining the value of rho L, which is denoted in this case by rho L. F upthrust is denoted by F, and here we have Vi and G. So the value of F we already know, which is given by 0.32. The value of G is given by 10. It's left to determine the value of Vi in order to determine the value of rho L. Knowing that S is completely immersed in the liquid, so the value of Vi is equal to V. Let's write this important statement. Since S is totally immersed in the liquid, and the liquid in this case, we don't know the nature of the liquid, whether it's water or alcohol. Then Vi is equal to V. Now let's rewrite this formula replacing Vi by V. The value of F is given by 0.32. The value of V is given by 2.7 times 10 to the power minus 5. The value of G is given by 10 because we are performing this experiment on Earth. So plugging this fraction on the calculator, it will give us 1185.19. Since everything is expressed in the SI, so the value of rho L will be in the SI, which is kilograms per meter cube. So the value rho L is equal to 1185.19 kilograms per meter cube. And by this we have finished solving this exercise. So that's it for me in this video, guys. In the next part 3, we'll complete solving exercises on this chapter.